Hello everyone and welcome to our 10.1 lesson on lines and segments that intersect circles. So this is our very first lesson on circles, and it's going to be, we're going to spend a full unit on it, but we're going to start class by filling out one of these small sheets, and so we're going to keep this out as we go over the vocabulary so that you have a picture of each of these things. By the end of the unit, you'll be very familiar with all of the different things in this picture. So let's start with some vocabulary. What is a circle? A circle, by geometric definition, is going to be the set of all points equidistant from a given point called the center. Equidistant is just a fancy way to say equal distance. So if you have ever seen a compass, we use a compass to draw a circle. And so this compass creates a circle because it has a center. You've got the little hard metal part that's in the middle that's on this point right here. And then you use this tool to spin it around, and every single one of these points that gets created is the same distance from this blue dot. So that creates this circle. And so that point in the middle is going to be called our center point. So what is our center point in my picture? The center of the circle is going to be point C. That just means that C is the same distance away from B as it is from D, as it is from E, G, F, and A. H is not on the circle, and so we're not going to say it's that same distance. But even if I added a point over here, a mystery point, it would still be the same distance away as long as it's on the circle. So what do we call this circle, the one that we have in our picture, my example? We would call this circle C. The symbol for that looks like this, the circle C. And the center would be the point, so point C. This point that is the same distance from all the points in the circle, and it's used to name the circle. So what controls the size of this circle? If I were to open up this tool a little bit more, that would make the radius bigger, and that would make the circle bigger. If I were to close this amount a little bit, that would make the circle smaller. And so the radius is going to control the size of the circle as well as the diameter. So what is a radius? A radius is going to be a type of segment. So let's underline that. It's a type of segment that has one endpoint at the center, at point C, and the other endpoint is on the circle. Okay, so one of my examples in my picture is going to be CB, starting at C, going to B. That is a radius of this circle. So that is going to be the same in length as it is from C to D. That is also a radius because it has one endpoint on the center, one endpoint on the circle. So C to D is going to be the same in length. And then C to A is going to be the same in length. The radius is the same all the way around that circle. So all of those are radii of the circle, and they are all congruent to each other. So that is the radius. It's highlighted in purple in my picture. Okay. All right, what is a diameter? A diameter is going to be a type of segment. So again, it says this word segment that contains the center of the circle, meaning the center is in the middle of the circle, and it has both endpoints on the circle. So it has to be a type of segment that goes through the center, but it stretches all the way across the circle. It's going to be the widest part of the circle. So in my picture, that is going to be the one starting at A, going all the way across to D, and it does go through center C. So we'd call that segment AD. That is the only diameter I have currently pictured. I could draw in another one. I could draw in another one by putting a point on the circle, having it go through the center and go all the way across. That's going to be the widest part of our circle, and that would be a diameter. The diameter is going to be the same all the way around the circle. So what is a chord? A chord, it uses this word again, is a segment whose endpoints lie on a circle. So basic definition of a chord, both of its endpoints have to be on a circle. So I could create a bunch of chords here to here, here to here, here to here, here to here. As long as it has the endpoints on the circle, you can call it a chord. So what have we talked about so far that is a chord? Let's look at what we talked about so far. What is a chord? A chord has to have both of its endpoints on the circle. So does a radius have both of its endpoints on the circle? No, it only has one. Is a diameter a type of chord? Yes, a diameter is a type of chord because both of its endpoints are on the circle, but it does not have to go through the center. So a diameter is a specific type of chord. So a chord is going to be anything that has a starting point and a stopping point on the circle. So I'm going to do a few different colors. All of these would be types of chords. So the diameter is a type of chord because it goes through the center, but it has both endpoints on the circle. But these other ones are just general chords. I kind of think of it like the guitar. Like you can kind of think of this like the whole, y'all are about to see a horrible drawing. The whole of a guitar, it's got chords that go through it, and we know that those are limited. Those don't go on forever. Okay, so what is a secant? Now all of a sudden I go from saying segment, segment, segment to the word line. Now this is going to be important. A secant is a type of line, and a tangent is a type of line. So we have a secant line and we have a tangent line. It's going to be important. A secant line intersects the circle at 2 points, meaning it touches it twice. So we have a green line in this picture and we have a pink line. Which line touches the circle twice? That is going to be our pink line. So FE would be our example. Instead of putting a segment over it, since it's a type of line, I'm going to put the arrows over it to show that it's a line. A tangent is going to be a line that intersects the circle at 1 point. So which one is our tangent line? HG is our tangent line. It only touches the circle once, and it touches this circle at point G, which is called our point of tangency. That's where it touches it. The point at which the tangent line and the circle intersect is going to be called our tangent line. And we're going to be learning some theorems about chords and lines and secant lines and all the different things on this picture, and arcs and areas and all of the things we've talked about so far. And so we'll learn more about that as we go, but this is going to be, for this lesson, this is our basic vocabulary that we need to know. Okay, so let's work on identifying some of these things. What is segment AB? So I already know it's not going to be a secant and it's not going to be a tangent because those are lines. So what is segment A to B? A starts on the circle, ends on the circle. So I already know that technically it's a type of chord, but this one specifically goes through that middle. It goes through the middle at point C. And so we're going to call this a diameter. This is a type of chord. I'm going to put that in parentheses. This is a specific type of chord, but it is specifically the diameter since it goes through the center. What is the segment A to G? Starting at A, going to G. Well, that is just going to be a generic chord because it does not go through the center, so I can't specifically call it a diameter, but it is a chord. It starts and stops. It has ending points that are on the circle. Okay. What is A to C? Let's change colors. A to C. A has one endpoint on the circle, and one endpoint is the center, so that is going to create something that is halfway across the circle that we call the radius. So A to C was the radius. And then they want to know, what is line DE? Whenever it says line, we know that's either going to be a secant line or a tangent line. So we have to pay attention. How many times does it touch the circle? It's got those arrows on the end of it. That only touches the circle once. So that is going to be our tangent line. I say tangent line. Where does it touch the circle? At point B. So that is going to be my point of tangency. And that will come in handy later whenever we start learning a few of our theorems. Point of tangency. Okay, what is point C? Well, point C is smack dab in the middle of this circle. That is going to be called the center. So this is the circle that's centered at C. And what is line A, G? Going from A, going through G. Okay, so this does say line, it's specific. So this is the line that starts at A, goes through G. So I know that that touches the circle twice, so we are going to call that a secant line. There is a chord that lies on top of that, starting from A and going to G, but the line that goes through it is considered a secant line because it touches that circle twice, once at A and once at G, and it extends beyond. Okay. We do just have some different things to notice about intersection of circles. You can have a circle that intersects another circle and you'd have 2 points of intersection. You could have 1 point of intersection. These are called tangent circles because they overlap at 1 point. Okay, 1 point of intersection if they're listed like this. Another picture we could do is where the circles touch, but they touch at 1 point. So that 1 point is on the circle of each of those circles, even though they're different. This is the one that is centered at A. This is the one that is centered at B, but that 1 point is on each of those circles. We could also have no points of intersection where they don't touch at all. Or we could have something called concentric circles, which is where they share a center. Share a center. So just because of that, we have some different common tangents. I think of common tangents like pieces of raw spaghetti. You have to figure out how can you lay these so they only touch each circle once. We have 4 common tangents. So this purple line only touches each of these circles once. This green line touches each of these circles once. And then you have the in-between pieces. So we could lay this piece of raw spaghetti so that it only touched each of these circles once here. And we could lay this piece of raw spaghetti so that it only touched each of these circles here. So that's 4 common tangents. Whereas if the circles are overlapping at a certain point, we only have 1 there. There's not space between like there is on this picture. We only have 1 point where each of them are touching. And then you have the above and below where it touches it once on top and then once on bottom. So 3 total common tangents. And then if the circles are overlapping, kind of like they do in a Venn diagram, you have no space in the middle. So you only have your top point, your top tangent line, and then your bottom tangent line. So that's 2 different common tangents. All right, so what are our tangent theorems? We're gonna have some theorems about tangents. A line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint. So this is a tangent line. How do I know it's a tangent line? Because it only touches the circle once at point P. So here's some theorems we're going to write about this. The first theorem says that that radius, O to P, is going to be perpendicular to A to B. O to P is going to be perpendicular to A to B. Meaning that I get to add, at this point of tangency, I get to add right angle markings. Those are perpendicular to each other. Okay? Which means if those are perpendicular to each other, if I were to actually draw in, which I'm going to, O to A, and I were to draw an O to B, what kind of triangles get created? Those are right triangles. So OAP, triangle OAP, and triangle OPB, are right triangles. That comes in handy because we know many theorems and many things about right triangles. We just have finished a whole unit on right triangles. Okay, so what do I know about the angles of those right triangles, or of triangles in general? They add up to 180. I also know a theorem that is the Pythagorean theorem that says if this is A, this is B, and then this is C, we know that A squared plus B squared is going to be equal to C squared. So this allows me to work with the Pythagorean theorem on this circle. Okay. We also have the external tangent congruence theorem. I think of this like the ice cream cone theorem. Tangent segments, so I have 2 different ones. I have one is tangent right here. B to A is only touching the circle once. And then we have B to C is only touching the circle once at point A and at point C. It says tangent segments from a common external point, so from this point B on the outside, from a common external point, are going to be congruent to each other, meaning that the distance from B to A is going to be the same as the distance from B to C. So B to A is going to be congruent to B to C. And I kind of see this like an ice cream cone. You've got a perfectly round, what looks like a circle of ice cream. That's this piece right here. And you've got a cone that's the same length on one side of the cone as it is on the other side of the cone. Okay? This only works if we know that both of these are going to be tangent lines from a common external point. So what does that mean? If I were to draw in a radius here and a radius here, we know that at point A, we're going to have a 90-degree angle, and at point C, we're going to have a 90-degree angle. So we would say that angle A and angle C are right angles. Okay, so what else do we know? We know that this is going to be, if you look at this, we know that this is going to be a kite. This is a quadrilateral. And so we know that what's left, there's 360 degrees in this full quadrilateral. So 360 minus 90 is going to give me 180 degrees for angle O plus angle B are going to be supplementary, which means that they add up to 180. So if you did 360 minus 90, that would give you 180 degrees for angle O plus angle B. So we have an obtuse angle and an acute angle. Those should have a sum of 180. So let's practice our tangent theorems in these pictures. Now you've got to read the directions. This is important. Solve for the indicated value given each diagram features tangents. If they didn't tell us that these were tangent lines, then I couldn't use my tangent theorems. So you've got to be told that they're tangent. So which one appears to be tangent in this first picture? DE, it's only touching the circle one time. Where is it touching the circle? At point D. So what do I get to add at point D? A right angle. I could add it on both sides if I wanted to. But really that's going to be significant because now I've created, here's a diameter, and then I've got this right triangle that is on top of the circle. Well, what do we know about triangles in general? They add up to 180 degrees. So if I want to find x, I can do 180. I can subtract the 90 I spent at the right angle, and I could subtract the 38 I spent at that other angle. And how many degrees are left? There would be 52 degrees left for x. 52 degrees. 52 and 38 will be complementary because I've already spent 90 in that triangle. All right, now this is interesting. It says assume that the lines that appear to be tangent are tangent. So from point X, we've got the distance from here, it's touching it once, should be the same as the distance to this part of the circle in green. We have to T is going to be the same distance to here. So the two pinks should be congruent. And then we have, let's do yellows, V to the circle should be the same distance as V to the circle on this side. And then we have W to the circle should be the same distance as W to the circle over here. So let's mark that using tick marks. 1 and 1, 2 and 2, 3 and 3, and then 4 and 4. All of those are common tangents to the circle, so the distances should be the same. So what does that mean if this little pink part is 1.2? I'm going to copy it to the other side. That means that this part, T to here, is 1.2. Well, that whole thing is 4.5. So what is 4.5 minus 1.2? 4.5 minus 1.2 is going to give me, did I mark that the same? 3.3. Yes, 3.3. So for that little yellow piece, 4.5 minus 1.2 gives me a total of 3.3. So this little piece is 3.3, and that makes sense because this side is 3.3, so that would have been an easier way to do it. But I just wanted to show you all that mathematically those are the same. 4.5 minus the 1.2 still gives me 3.3, so those match on each side. This purple piece is 3.1, so this purple piece will be 3.1. That full amount is 8.3, so what is 8.3 minus 3.1 left for green? That is going to give me 5.2 for each of these green pieces, 5.2 here and 5.2 here. So what is x to t? X to t is going to be 5.2 plus 1.2. 5.2 plus 1.2 is going to give me a total of 6.4. Okay. All right, we've got some tangent lines again. M to L is touching the circle once, so there's a 90-degree angle right here. M to N is touching the circle once at point N, so there's a 90-degree mark right here. So what do we know about 117, that's obtuse, and x, that's acute? Those are going to be supplementary to each other. So we're going to say that x plus 117 should have a sum of 180. You could also do 360 minus 90 minus 90 minus 117, and you'll get x. So what is left for x? That is going to be 64 degrees, which makes sense because that is an acute angle. All right, and then our last tangent problem. A is a tangent line. It's touching the circle once at point B. So I'm going to mark that. And then A to D is touching the circle once at point D. So I'm going to mark that. What do we know about the lengths of those two tangent lines coming from the same external point A? We know that those should be congruent. So 2x plus 7 should be the same length as 5x minus 8. So I can set those lengths equal. 2x plus 7, the left side of the cone, should be equal to the right side of the cone. I see this like ice cream cones. So 3x is equal to 15, so x is equal to 5. What is AB? It's going to be 2 times 5 is 10, plus 7 is 17. You should be able to plug it into the other one and get 17 as well if you did it right. 5 times 5 is 25, minus 8 is also 17, so I know I did that right. So those are our tangent problems using our tangent theorems. All right, we've got a few more. It says determine whether the segments below are tangent. So we were told that they were tangent in the previous examples. Now we're determining whether they're tangent. Well, if they're tangent, then we should have right angles created at point A here, and at point A here. So how do we tell if those are right angles? We're going to use the Pythagorean theorem because we know that if this is in fact a right triangle, then a squared plus b squared should be equal to c squared. A squared plus b squared should be equal to c squared if this is in fact a right angle. So I'm going to put a question mark on it because we're not positive that it's a right angle. The math has to work out for this to be a right angle. So let's plug it in. 3 squared plus 4 squared. Is that in fact equal to 5 squared? So I'm going to erase this equal sign and let's see. What is 3 squared plus 4 squared? That's going to be 25. What is 5 squared? That's also going to be 25. So because these are both equal, then yes, this is a right triangle. So are these tangent? We would say yes, that is a right angle. Okay, let's do that again here. Now you have to be careful here because we've got our unknown angle in question at point A. Is it a right angle? We're trying to find out. But this time I'm missing my hypotenuse. I need what is this whole thing? So what is this whole piece? Well, we do have a radius here. What is the radius? The radius is 11. So what is this radius going to be? Also 11. So I can mark an 11 there. So what is that whole thing? What is 11 plus 5? That is going to give me a hypotenuse of 16. So when I fill this in, I'm going to call this piece A, this piece B, and this piece my C. So we're going to plug this into a squared plus b squared. We're going to see how it compares to c squared. It should be equal if it is going to be a right angle. So 14 squared plus 11 squared, and we're going to see how that compares to 16 squared. 14 plus 11 squared is going to be 317. 16 squared, I think, is 256. So are those equal? No, those are not equal. And so since those are not equal, I'm going to do an equal sign and slash it out. Since those are not equal, we know that that is not a right triangle. And in fact, that is going to be an acute triangle. And so this is going to be not a right angle. Not a right angle. So I'm going to cross that right angle out. That is not a right triangle, so this line is not tangent, meaning it's either not, the point A is either not on the circle, or it's going to be touching it more than once. Okay? Okay, now we want to see if a squared plus b squared is equal to c squared. So this time they give me the full amount. We're going to see how does 8 squared plus 15 squared compare to c squared. So how does 18 plus 15 squared compare to 17 squared? This is 289 on this side. This is 289 on this side. Because this is equal, this is in fact a right angle. So this is a yes. So this one was a no. But you have to confirm with math, with theorems that we've learned before, if these are tangent lines. Because sometimes it's going to be hard to tell if they do touch, if they don't touch, or if they touch more than once. All right, last but not least, we've got our chord theorems. So we do have quite a few chord theorems. Chord theorems seem hardest to describe, but they're actually the easiest to see. So if we know, this is what it says. I'm just going to read it how it's written. If E to O, this distance, from the center to a point on that chord, is congruent to F to O, then we know that those chords are going to have to be congruent. So just meaning if you swung AB around, it would be perfectly on top of CD. So I'm going to write that out. Those chords are going to be congruent. So A to B is going to be congruent to C to D. So if they're the same distance away from the center, then those chords are congruent. We also have a theorem that says if you have a chord AB, you can see that's a diameter, that is perpendicular to CD, cutting it at 90 degrees. So I'm going to do that right here. That's at 90-degree angle right there. I'm going to underline that a little bit more so you can see it. If that is a right angle, then you know that that chord gets cut in half, meaning that C to E is going to be congruent to D to E. So that diameter is going to cut this chord in half. It cuts the circle in half, but it also cuts this chord in half. And you can see that we've got the top half of the circle would fold directly onto the bottom half of the circle. But we can also go backwards. We know if those are congruent, if C to E is marked congruent to D to E, that must mean that these are going to be perpendicular. So that means that I get to add a right angle. So that would mean that C to D must be perpendicular to A to B. So I get to add a right angle here. Those are perpendicular to each other. Okay? And I could add a right angle all the way around, and I'm actually going to do that in this picture. Those are going to be perpendicular to each other. So that just means it is going to be, that is the center fold of the circle, and so that is going to be, you could fold the top onto the bottom, and there are 4 right angles right there, and that will come into play in a minute. Okay, let's look at our chord problems. Solve for the indicated value. So what do I have marked in this picture? I have 12 marked, so I've got a chord right here. I've got 12 marked on this side, and so that means that there's going to be 12 on this side as well. So that entire chord is going to be 24 in length. And then I've got a 9. This little piece is 9. This little piece is 9, which means that they're the same distance away from the center. Since those are the same distance away from the center, that means that those chords are going to be congruent. So what is X? It has to be congruent to the other chord. It's also going to be 24. So since they're the same distance away from the center, that's the only reason I was able to do that. Since both of those were 9, that means that those chords are congruent. Okay, this one kind of works backwards. We've got the 2 congruent marks here, so that whole thing is 8. This whole thing is 8. So if those chords are congruent, what does that mean about the distance to the center? That means that that is going to have to be the same. So if this little piece is 3.2, what is the distance to the center on this one going to be? Also 3.2. Okay. Now I've got a chord. It has 2 endpoints that lie on the circle that is perpendicular to a KN, which is going to the center of this shape. So what does that mean? that means that what we can do is we can use some Pythagorean theorem because I've got a right triangle. So if this whole blue thing is 14, what does that mean half of the blue thing is? Because it cuts it in half. That means that that's going to be 7. So both of these pieces are 7. And now to find the radius of this shape, I can use some Pythagorean theorem. I'm going to say a squared plus b squared equals c squared in this right triangle. So I'm going to highlight that so you can see which one I'm talking about. Here's the right triangle. And so I'm going to plug in those pieces. I'm going to say 3 squared plus 7 squared is going to be equal to that radius squared. And so what we're going to get, 3 squared is 9, 7 squared is 49. And so when I do r squared, that's going to end up being 9 plus 49. That's going to give me the square root of 58, which is going to be about 7.6. So the radius of this is going to be about 7.6. Okay. This last one is going to be the hardest one on here. And so we've got a circle, and that circle is centered at this point right here, so it doesn't really have a letter on it. But I want to pay attention to all the different marks here. We do have a diameter, first of all, 12. So what does that mean about each individual of those pieces? That means that those individual pieces are both going to be 6. Remember that a radius is the same all the way around the circle. And then we've got this little piece right here that is 3 units away from this chord. So here's the chord. That chord is marked the same on each side. So know that it cuts it in half. And so what can I do with these pieces? Well, we want to find x. Well, there's no other chord that's marked the same length or distance away from that. So I can't just copy the other chord like I did on this first problem. But what I can do is I can take this radius that is the same all the way around this shape, and I can copy that radius to here in order to close the triangle. I'm just swinging it around. That still is going to have a length of 6. The length of 6 would be anywhere on the shape. So I could put a 6 here or here, anywhere on the shape. So I'm just copying that blue radius to close this triangle, and now I can use Pythagorean theorem. So that is going to be x squared plus 3 squared is equal to 6 squared, where 6 is my hypotenuse because it is across from that right angle. Where's my right angle? My right angle is right here. And so that is my hypotenuse. And so what I'm going to do is I'm going to do 6 squared minus 3 squared. So I'm going to subtract 3 squared from both sides. 6 squared is 36. 36 minus 9 is going to give me 27. So x is going to be the square root of 27. What is the square root of 27? It's going to be about 5.2. So if I wanted to know how big that chord was, I could put 5.2 here. I could put 5.2 here. That whole chord would be about 10.4, but they only asked me for x here. So that is a lot of theorems, a lot of information. So we are actually going to be practicing that tomorrow for our 10.1 homework. We're just getting the vocabulary and the theorems down today.